Hello, everyone. Happy Monday. I hope that you had a great weekend. Unfortunately, my son is sick and he's going to be home from school today, so I'm going to be staying with him and I will not be able to make it to class today. So, what that means for us is that one, we'll be doing a video lecture that you can kind of start and stop and watch it on your own time, at your own pace. And two, it also means that I will not be able to give the homework for quiz that I was planning today on Monday. Instead, I'm going to be giving you that quiz on Wednesday, which is February 15th. We will have a quiz over homework 4 material. So you'll have a couple more days to study for that and get ready for it. But the quiz will be on Wednesday. So we will start covering homework 5 material in this lecture. We will continue covering homework 5 material in class on Wednesday the 15th and on Friday the 17th. And that means that your homework 5 in ALEX will be due on Sunday, February 19th by midnight. That's kind of what's coming down the line for you tomorrow and through the week. And just a heads up, Joseph will be having an SI session this evening. It's on Monday, February 13th at 5 p.m. on the 5th floor of the Academic Learning Center, room 5102. So without further ado, let's get started. So just going to set myself a timer here so that I don't run way over time here for you. Okay, so let's start working through homework 5. So we're continuing on with trig functions, and we're going to get more in depth with these and start studying them a little deeper. So the first thing that I want you to do is this warm up. So do me a favor, hit the pause button on this video. I want you to find all 6 trigonometric function values of both alpha and beta. So hit pause, go ahead and do that, and we'll come back together in a second. Okay, hopefully you've had a chance to practice these. So let's rock through these. In order to find all 6 trig functions of both of these angles, I'm going to need to know what this side is. So in order to find that, we're going to use the Pythagorean theorem. So we're going to have 8 squared plus this side squared is equal to 17 squared. So we're going to have 64 plus b squared is equal to, my brain's not working, I'm going to put that in my calculator so I don't screw it up, 289. Okay, so that means that b squared is equal to 225, and that means that this side is 15, which is the square root of 225. So Pythagorean theorem says that this side is 15, so now we can go ahead and rock through each of these. So let's start with alpha, and we will let's see, we'll do cosecant of alpha, we'll do the secant of alpha, and we'll do the cotangent of alpha. And then we'll do each of these for beta as well. Sorry, the sine of beta, the cosine of beta, the tangent of beta, the cosecant of beta, the secant of beta, and the cotangent of beta. Okay, so let's start with alpha. So this is our angle of reference here. That's where our eyes are looking. So sine is going to be the opposite side, which is 15, over the hypotenuse of 17. The cosine of this angle alpha is going to be our adjacent side, which is 8, over the hypotenuse, which is 17. The tangent of alpha is going to be our opposite side, which is 15 over our adjacent of 8. The cosecant is going to be hypotenuse over opposite. It is the reciprocal of sine, so this is going to be 17 over 15. Secant is hypotenuse over adjacent. It is the reciprocal of cosine, so this guy is going to be 17 over 8. And the cotangent of alpha is going to be adjacent over opposite. It is the reciprocal of tangent, so that's going to be 8 over 15. And now we'll do the same thing for beta. So now when we go through our trig functions for beta, this angle is our point of reference. So to find the sine of beta, we're going to take the opposite side. The side opposite angle beta is now 8 over the hypotenuse, which is still 17. So now we'll do the cosine of beta. That is the adjacent side, which for beta, the adjacent side is 15 over the hypotenuse of 17. The tangent of beta is the opposite side, which is 8 over the adjacent side, which is 15. Cosecant is hypotenuse over opposite, the reciprocal of sine. So this is 17 over 8. The secant is hypotenuse over adjacent. It is the reciprocal of cosine. So this guy is 17 over 15. And the cotangent of beta is adjacent over opposite, the reciprocal of tangent. This one is 15 over 8. Okay, great. So you may be asking yourself, why did she make us do all of this? We know how to take trig functions. Well, you're right, you do know how to take trig functions, and it's good practice just to kind of run through these, but I also want you to notice some connections between the trig functions of two angles in the same triangle. Now, remember that these two angles have to add to 90 degrees or pi over 2 radians. The reason for that is because all three angles in this triangle have to add to 180, and we have a right angle, which is 90 degrees, or pi over 2 radians, which means that we only have 90 degrees left for these two. So alpha and beta must be complementary. They must add to 100 or to 90 degrees or pi over 2 radians. And notice the connections here. The sine of alpha is the cosine of beta. The cosine value of alpha is equal to the sine value of beta. Those two, excuse me, those values switch. Because the opposite side of alpha is the adjacent side of beta. And the adjacent side of alpha is the opposite side of beta. So that's why these two switch. And then after that, hopefully you'll notice some connections here. The tangent of alpha is the cotangent of beta. The cotangent of alpha is equal to the tangent of beta. And the secant and cosecant values are also opposite. So this is going to give us rise to something that we call co-function identities. Now, co-function identities, sometimes these are called complementary identities or complement identities. We're going to get into what an identity is much more in detail later on in the semester. For right now, just know that an identity is an equation that is always true, no matter what value the variable takes on. So, I'm going to give us a triangle here to give us a frame of reference. So it's got to be a right triangle to have trig functions. I'm going to call this angle theta, which means that this angle here must be 90 degrees minus theta or pi over 2 minus theta, depending on whether theta is in degrees or radians. So with what we just noticed here, our cofunction identities say that the sine of theta is equal to the cosine of this other angle in the triangle. I'm going to leave everything in degrees for now, and I'll just kind of make a note at the end for how to change it for radians. But the sine value of one angle is equal to the cosine value of the other angle in the same right triangle. And we kind of noticed that in this example that we just went through. Similarly, the cosine value of theta is going to be the sine value of this other angle, its complement. And we said the tangent value, this was the same as the cotangent value of that other angle in the triangle. Similarly, that means that the cotangent value of theta is going to be the tangent value of its complement. We'll start with the cosecant of theta. That's going to be the secant value of its complement. And the secant value of theta is equal to the cosecant value of its opposite. These are the same relationships we noticed in the example above. We're just generalizing it. Now, this is all in degrees. This is what you would use if theta is measured in degrees. If theta is measured in radians, you're just going to change all of these 90 degrees to pi over 2 if theta is in radians. That's really the big thing that's going to change here. Okay, so these are called cofunction identities again, or sometimes they are called complement identities. Let's try these. Now, especially in ALEKS, they don't actually want you to put any of these values into a calculator. We're not looking for the value of these trig functions. We want to use a cofunction identity to write an expression that means the same thing. So the sine of 15 degrees, they do not want you to put this in a calculator and tell them what the sine of 15 degrees is. We are looking for an equivalent expression. So with the identities that we just went over, the sine of 15 degrees, we can write an equivalent expression as the cosine value of its complement. So that means that the sine of 15 degrees is going to be equal to the cosine value of the complement of 15 degrees, which is 90 degrees minus 15 degrees, right? The other angle in the triangle. And if we subtract 15 degrees from 90 degrees, we get 75 degrees. Again, ALEKS is not going to want you to put this in a calculator and get a value. It just wants you to say, oh, the sine of 15 degrees, that's going to be exactly the same as the cosine of 75 degrees. You can check that in a calculator, put both values in a calculator, and you will notice that you get the exact same value. But we are just looking for the other trig function that's equivalent to this one. That's all we're doing. So let's rock through these next few. The secant of pi over 10. I'm looking for an equivalent expression to this one. So the secant value of pi over 10. Well, in our triangle, the secant value switched with what other trig function? The secant value switched with cosecant. So I know that I'm going to change this into a cosecant. Now the question is, it's going to be the cosecant of what angle? Well, the answer to that is it's going to be the other angle in a right triangle. And again, the two non-right angles in a triangle have to add to 90 degrees, or pi over 2 radians. So the angle that is going to be equal to the cosecant of is going to be whatever is left over when I subtract pi over 10 from pi over 2. So to do this, I'm going to get any common denominator. So I'm going to have the cosecant of 5 pi over 10, getting a common denominator, minus pi over 10. This is going to be the cosecant of 4 pi over 10. I can simplify that a little further. This is going to be the cosecant of 2 pi over 5. That's the value that we're looking for. Again, not looking for the exact value, I guess, so I should say that's the expression that we are looking for. Okay, next one, cotangent. Well, I know the cotangent, that switches values with tangent. So I just have to figure out what the angle is, and it's going to be the other angle in a right triangle that's not the 90 degrees. So I'm going to take pi over 2 and subtract pi over 12 to figure out what that other acute angle in the triangle would be. And now I just have to fight through the arithmetic here. So my common denominator is 12. So I'm going to multiply pi over 2 by 6 over 6. That's 6 pi over 12 minus pi over 12. So this becomes the tangent of 5 pi over 12. And that's as simple as she goes. So that is the expression that we're looking for. The cotangent of pi over 12 is equal to the tangent of 5 pi over 12. And then the last one here, the cosine of 31.8 degrees. This is going to be equal to the sine, because again, cosine and sine switch values. And so this is going to be the sine of the other angle in that right triangle. So it's going to be 90 degrees minus 31.8 degrees. When we subtract 31.8 degrees from 90, you get 58.2 degrees. This is the expression that we are looking for. Okay, so again, these are called co-function identities. You're just going to use these for now to rewrite a given expression as an equivalent expression with the other trig function. Okay. All right, so we're going to switch gears a little bit. We're going to go back to working with angles in standard position. Now, from here on out in the course, quadrants are going to play a big role in what we do in this course. So what a quadrant is, if you draw a Cartesian plane like we have here, the x-axis and the y-axis cut this two-dimensional space into 4 parts. We call these quadrants, and we number these in a kind of standard way. This top right corner here, where x and y are both positive, this is quadrant 1. This top left corner, where x is negative and y is positive, this is quadrant 2. Bottom left, where x is negative and y is negative, this is quadrant 3. And the bottom right, I bet you've guessed, this is quadrant 4. That's where x is positive and y is negative. So this is the standard numbering for quadrants. I'm programmed to use Roman numerals, but I'm not going to count off if you use kind of our standard numbering system. You can really kind of do whatever you want, but I'm programmed to do Roman numerals. So that's kind of what I'm going to stick with. And I think usually you'll see them with Roman numerals, but it doesn't make it wrong to use other, like I think they're Arabic numerals. So biggest thing is know which quadrant is which. So you start in the top right corner and go around counterclockwise. So quadrant 1, 2, 3, and 4. And they're labeled this way because in standard position, those are the quadrants that a positively rotating angle, that's the order that it rotates through the quadrants in. Okay, so these are going to come into play because basically angles in a quadrant kind of all act the same way. And so we can kind of group angles together by quadrants because they are trig functions, and angles kind of act the same way in those quadrants. So we're going to start with reference angles. That's the first thing that we're going to kind of do with our quadrant system. So a reference angle, basically, this is the acute angle between the terminal side of another angle and the x-axis. So an angle is going to have a reference angle. The reference angle is the acute angle that the original angle's terminal side makes with the x-axis. Now, the fact that this is the x-axis is hugely, hugely important here. We will always come back to the x-axis. The x-axis is our home base. The y-axis will not be used as a kind of home base. It's always going to come back to the x-axis. I cannot kind of emphasize that enough. So let's start with an angle. So we're going to do this for each quadrant. I'm actually going to start in quadrant 2 because I think quadrant 2 is clearer than quadrant 1. Quadrant 1 is kind of strange. So let's say I have an angle in standard position where my initial side is along the positive x-axis. And let's say my terminal side rotates all the way through quadrant 1 and into quadrant 2, right? So my terminal side is in quadrant 2. So what that means is that my angle here is this guy in standard position. Now, the reference angle here is going to be the acute angle between the terminal side of this thing and the x-axis. So where is our reference angle in this picture? Well, it's from the terminal side to the x-axis, and it must be an acute angle. It's always going to be the smallest angle between the terminal side of an angle and the x-axis. So here, this guy down here is my reference angle. I'm going to call him theta ref. So that's where my reference angle lives in quadrant 1, or sorry, quadrant 2. Let's come back to quadrant 1 now. Let's say I have an angle in standard position. So my initial side is on the positive x-axis. Let's say my terminal side rotates into quadrant 1 and stops there. That means that this is my angle theta. Okay, so where is my reference angle in quadrant 1? Well, it's going to be the smallest angle between my terminal side and the x-axis. That means this angle is also my reference angle. In the first quadrant, my original angle and my reference angle are the same. That's the only quadrant where that will happen. Like we talked about in quadrant 2, this reference angle isn't in it's in a separate position. Let's come to quadrant 3. What if my angle starts in standard position? So I have my initial sides on the positive x-axis. Let's say my terminal side rotates into quadrant 3. So that means my original angle is all of this because my terminal side started here at my initial side and rotated all the way around into quadrant 3. Okay, so that's what theta looks like. Where is theta's reference angle? Well, it's the smallest angle between my terminal side here and the x-axis, which is this angle right in here. That is theta ref. Okay, let's try quadrant 4. So now have our initial side, and let's say my angle starts and rotates all the way through the first 3 quadrants and ends up in quadrant 4. So my terminal side ends up right here. So theta rotated through all of this and stopped here. Where is my reference angle? It's the smallest angle between my terminal side and the x-axis. Well, that would be right here. There's my reference angle. Okay, we're going to figure out how to calculate these, but let's start with examples and we'll come back up and make these more general. So let's start with number 1 here. We're going to draw each angle in standard position and calculate the reference angle. Okay, so the first thing I got to do is draw a picture here because that's going to be helpful for us. 210 degrees. Okay, this is in standard position. So my initial side starts here on the positive x-axis, and my terminal side rotates through 210 degrees. So we got to figure out where this thing is. Let's see. So I know 90 degrees is up here, 180 degrees is over here, 270 degrees is down here, and then all the way around would get us to 360. So 210 is between 180 and 270. That means my angle theta is going to rotate all the way through quadrants 1 and 2. It's going to get into quadrant 3, and I'm going to go a little bit into quadrant 3. Here is 210 degrees. That's my angle theta. Okay, so where is my reference angle in all of this? Okay, so my reference angle is here. It's the smaller angle between my terminal side and the x-axis. How big is that? Well, sorry. Let's try to go back here. So my reference angle, I have to figure out how big that is. Well, 180 degrees would start here and just go all the way to here. I go through 180 degrees, but then my reference angle is how much past 180 degrees I go. So to find my reference angle here, I'm going to do my angle theta, and I'm going to subtract 180 degrees from that. Because that's going to tell me how much past 180 degrees I go. It's going to tell me how many degrees after 180 I have left. So when you do this subtraction, we get that our reference angle here is 30 degrees. And coming back up here, the thing is that all angles in standard position that are positively rotating, this is how we're going to calculate our reference angle in quadrant 3. All of our quadrant 3 reference angles are going to have this relationship. So here in quadrant 3, you calculate your reference angle by finding your angle theta minus 180 degrees, or theta minus pi radians. Sorry, that's not super clear. I want to rewrite that because that got a little close. So that's how we're going to calculate our reference angles in quadrant 3. Okay, let's try the next one. Okay, number 2, 11 pi over 6. So first of all, we have to figure out where this angle lives. Okay, so this is in radians. That's going to be harder for our brain to do. Okay, so I know that the top here is 90 degrees. 90 degrees is pi over 2 radians. That should already be in your programming. Over here on this left side, that would be 180 degrees. That's going to be pi radians. Down here, this one might not be in your programming yet. You might not have had this one memorized yet. but I want you to put this one there. Down here at the bottom, this is 270 degrees, or 3 pi over 2 radians. It's 1.5 pi, essentially. 3 pi over 2 radians is down here. And all the way over here, that's 360 degrees, that's 2 pi radians. Okay, so this is kind of what everything looks like in radians, but radians are fractions, and that's confusing to me. So I'm going to change all of these to have the same denominator as the angle that I'm given. So I'm going to change all of these into an equivalent fraction over 6. So that means I'm going to make all of these equivalent fractions with a denominator of 6 so that I can see where 11 pi over 6 lives more clearly. Let's start up here with pi over 2. To get a denominator of 6, I'm going to multiply top and bottom by 3. That means pi over 2 is 3 pi over 6. Pi over 1 to get a denominator of 6. Multiply top and bottom by 6. That turns into 6 pi over 6 radians. Down here, 3 pi over 2, multiply top and bottom by 3. That turns into 9 pi over 6 radians. And on the right side here, 2 pi over 1, multiply top and bottom by 6. That turns into 12 pi over 6 radians. Okay, so where does 11 pi over 6 radians live? Well, we would start here. We would rotate all the way through 3 pi over 6. That's not big enough. We would keep rotating through 6 pi over 6. Not big enough. We still have more left. We would rotate down to here, 9 pi over 6. We still are bigger than that. We would rotate all the way into quadrant 4. This is where 11 pi over 6 radians lives. I always do this, 11 pi over 6 radians. So that's how big our original angle is. 11 pi over 6 rotates into quadrant 4. So where's our reference angle? Because that's what we need to find. Reference angle is right here. Small angle between the terminal side and the x-axis. How big is that? Well, so all of this rotates through 11 pi over 6. If I went around the whole circle, I would be at 12 pi over 6. Basically, my reference angle is how far short of 12 pi over 6 am I? How far short am I of a whole circle? So to find that, I'll come down here. I'm going to take the whole circle, which is 2 pi, and I'm going to subtract from that my angle theta. That's going to tell me how much is left over for this little part between my terminal side and the x-axis. So again, common denominator, this was 12 pi over 6. My angle theta was 11 pi over 6. When I subtract those, 12 pi minus 11 pi, that is 1 pi over 6. That is my reference angle. It is pi over 6 radians. And similarly, any angle in quadrant 4 is going to act this way. So if I come back up here in quadrant 4, here I am in quadrant 4, to calculate your reference angle, we're going to have to figure out how far short of a whole circle we are. So we are going to do 360 degrees minus your angle theta if we are in degrees, or if we are in radians, we're going to do 2 pi minus theta. Our reference angle is how far short of the whole circle we are, so we're going to subtract our angle from the whole circle to find those. Okay. Number 3. Let's come down here and see where is 45 degrees. Okay, so we're in degrees, so I know this is 90 degrees, this is 180 degrees, this is 270 degrees, this is 360 degrees. Where's 45? Well, it's halfway between 0 and 90 degrees, so I am up here in quadrant 1. That is my angle theta. Okay, so now I have to figure out what my reference. That's a theta, theta ref. So my reference angle in quadrant 1 is going to be the angle between my terminal side and the x-axis, which is this guy right here. That's my reference angle. Notice that's the exact same angle that I just rotated through. So in this case, my reference angle is my original angle. These two are the same. So my reference angle is going to be 45 degrees, the same as my original angle. And that's actually going to be the case for any angle in quadrant 1. So just like we said up here in quadrant 1, the all of your angles in quadrant 1 will be acute. So your reference angles, the smallest angle between your terminal side and the x-axis, is going to be the same angle you just rotated through. So in quadrant 1, to find your reference angle, it's exactly the same as your original angle. Doesn't matter if it's in radians or degrees, it's going to be the same. All right, let's slide through this last example here. 3 pi over 4. Okay, we're in radians again. So we got to figure out where this thing lives. Again, in radians, up here we're at 90 degrees. That's pi over 2 radians. On the left side, we're at 180 degrees. That's pi radians. At the bottom, we're 270 degrees. That is 3 pi over 2 radians. And here on the right, we're 360 degrees or 2 pi radians. To figure out where 3 pi over 4 lives, I'm going to want to turn all of these into equivalent fractions with a denominator of 4 so that I can compare this to everything that I have here and it'll make more sense. So I'm going to turn all of these into equivalent fractions with a denominator of 4, and we'll see where 3 pi over 4 lives. So let's start at the top. Pi over 2. To get a denominator of 4, I'm going to multiply top and bottom by 2. Over here on the left, I'm going to multiply top and bottom by 4. Here at the bottom, 3 pi over 2, I'm going to multiply top and bottom by 2, so that becomes 6 pi over 4. And 2 pi over 1, I'm going to multiply top and bottom by 4, so that's 8 pi over 4. Again, I'm just multiplying all of these to turn it into an equivalent fraction with a denominator of 4 so that I can more easily compare my fraction with kind of the boundaries of these quadrants so that I can figure out which quadrant this angle is going to land in. So where does 3 pi over 4 live? Well, 3 pi over 4 is going to be halfway between 2 pi over 4 and 4 pi over 4. It's going to be right here. So I'm going to rotate from standard position all the way through here to quadrant 2. This is 3 pi over 4. And so my reference angle then is going to be the smallest angle between my terminal side and the x-axis. My reference angle is this guy right here. So how do I find it? How do I calculate that? Okay, so 3 pi over 4 goes all the way through here. And I know that if I rotated all the way over to here, to my back, all the way back to the x-axis, I would be at pi radians. But I don't get all the way there. Notice my theta ref is how much further from theta I would have to go to get to pi radians. So to find my reference angle, I'm going to have to take pi radians and subtract my angle theta. I want to know how much further from theta do I have to go to get to pi. So I'm going to subtract theta from pi to see what's left over. So that means I'm going to take pi radians and subtract my angle theta, which here was 3 pi over 4. I'm going to get a common denominator and do 4 pi over 4 minus 3 pi over 4. And when I do that subtraction, this is going to be 1 pi over 4. That is my reference angle. Sorry, I know it's kind of tight down here, trying to squeeze that into a small space. So my reference angle here is pi over 4. And again, this is how it's going to work for any angle in quadrant 2. So if I come back up here to my diagram, any angle in quadrant 2, to calculate our reference angle, we need to figure out what is left between our angle theta and this guy right here, which is 180 degrees or pi radians. So theta ref is going to be 180 degrees minus theta, or if we are in radians, it will be pi minus theta. How far short of 180 degrees are we? That will tell us our reference angle. All right, so this is how we calculate reference angles. With all of these were positively rotating angles. What if our angles aren't positively rotating? So like number 5, negative pi over 3. How do we find our reference angle at negative pi over 3? Okay, well, let's draw it and figure it out. So negative pi over 3 radians, where does that live? Well, I know it's going to be a negatively rotating angle, and it's going to rotate through pi over 3 radians, which is 60 degrees. So I'm going to be down here. This is negative pi over 3 radians. Where's my reference angle? Well, my reference angle is going to be the angle here between my terminal side and the x-axis. So that's going to be the same size angle as I just rotated through, but your reference angle is always going to be a positive acute angle. So that means my reference angle here is going to be a positive pi over 3 degrees. It'll be the same size as what I just rotated through, but it's always positive and it's always acute. Now, notice that our formulas here for something in quadrant 4 didn't quite work with what we had. The reason for that is because the angle that we were given here was negatively rotating. These formulas only work for positively rotating angles in standard position, specifically ones that are between 0 and 360 degrees in one rotation of the circle. So if you work better, like if problem solving here and trying to figure out where your reference angle is, if that doesn't work for you, what I want you to do is find a coterminal angle with what you're given that is positive between 0 and 360 degrees, or between 0 and 2 pi. So here, to find a coterminal angle, and I'm actually going to switch colors here so you can see that it's a different way to do this. I'll do the other way in red. So we could also find a coterminal angle here. Remember, to find a coterminal angle, you're going to add or subtract a whole rotation around the circle. Since this is negative and I want to go positive, I'm going to add a whole rotation. I'm going to add 2 pi. So we're going to have negative pi over 3. We're going to add to that 2 pi, which is 6 pi over 3. And overall, I'm going to get a positive coterminal angle of 5 pi over 3. Once I have a positively rotating coterminal angle between 0 and 2 pi, I can now come back to my formulas and I could apply this. So that would mean that my reference angle here is going to be 2 pi minus 5 pi over 3, which would be 6 pi over 3 minus 5 pi over 3. My reference angle is pi over 3. Exactly the same thing that I got before, but you can use your formulas that way. Um, so if what you're given is not a positively rotating angle between 0 and 360 degrees, find a coterminal angle that is a positively rotating angle between 0 and 360 degrees. Then you can apply these formulas to it. Okay, we will do one more. How about this one? 8 pi over 3. Okay, so to figure out where this lives, I'm going to do, oh, sorry, I guess that is 0, but we'll want to do, so this is pi over 2, pi, 3 pi over 2, and 2 pi. And I'm going to have to turn everything. We're going to have to get common denominators here. All of these are over 2. What I have is over 3. To compare these guys, I'm going to have to put everything into fractions with a denominator of 6. Okay, so to do that, pi over 2, that is going to be 3 pi over 6. That's a 3. Over here at pi, multiply top and bottom by 6. That's 6 pi over 6. Down here, 3 pi over 2, multiply top and bottom by 3. That's 9 pi over 6. And 2 pi over 1 is 12 pi over 6. And our original angle here of 8 pi over 3, multiply top and bottom by 2. This is 16 pi over 6. So where is this located? Ooh, so we are going to rotate all the way around the circle, and we still have some left. All the way around the circle would be 12 pi over 6. We have to rotate through 16 pi over 6. We would keep going, and we would go another 4 pi over 6. So notice we would rotate into here. Does that make sense? 16 pi over 6, whole circle is 12 pi. We have another 4 pi over 6 to go. The top is only 3 pi. We would have one more to go to stop here. Now, if your brain can't do that math and you are struggling with that, what we're going to do is we are going to subtract to find a coterminal angle that is between 0 and 2 pi. Now, because this rotates a whole circle and then some, I'm going to subtract 2 pi to get a coterminal angle between 0 and 2 pi. So I'm going to do 16 pi over 6 minus 2 pi, which is 12 pi over 6. That gives me an angle of 4 pi over 6. That is my positively rotating angle between 0 and 2 pi that's coterminal with what I have. 4 pi over 6 starts here and rotates up here because that is between 3 pi over 6 and 6 pi over 6. So I am in quadrant 2. And now that I have a positively rotating angle between 0 and 360, now I can use my formulas. And I would come up here and say, oh, I have an angle in quadrant 2. To find my reference angle, I'm going to do pi minus theta. To find my reference angle, I'm going to do pi minus theta. And I'm going to have 6 pi over 6 minus, that's a 4 pi over 6. That means my reference angle is 2 pi over 6 or pi over 3. My reference angle, which is right here, is pi over 3. Okay, and like we said here at the bottom, we will use reference angles to find trig values for angles that are larger than 90 degrees. We will start working with that on Wednesday. But when you come to class on Wednesday, I want you to be very familiar with reference angles, what they are, and how to find them. And I also want you to be ready for a quick quiz on homework 4 material. So, have a lovely day, and I will see you back in class on Wednesday.